Carolina Santiago Nava, and today what we're going to do is an experiment called How Fast Can Dominoes Move? The phenomenon that will be used for this experiment is uniform linear motion, which is also known as rectilinear motion. It refers to motion with a constant velocity or a velocity that will not change over time, all this along a straight line. The first of Newton's law, the law of inertia, states that every object will remain at rest or in a uniform motion in a straight line unless compelled to change, a state by the action of an external force. This means that if there is not a force acting upon an object, then the object will maintain a constant velocity or remain at rest. But if some type of force is applied, this will change. And this is what we intend to prove in this experiment while using dominoes. The variables used in this experiment would be the following. The velocity, the fall, and the time that it will take will be the dependent variables. The distance between the dominoes is an independent variable, and the object that will intervene is one as well. And lastly, the size of the dominoes and the total distance are the control variables. Now, for the materials that we will be using, you will need 15 pieces of dominoes or something similar. As you can see here, I'm not using domino figures, I'm using Jenga pieces. The important thing here is that they are small and that they are about 1 centimeter wide at most. Then, you will also need a 13 centimeter ruler, a toilet paper roll, an eraser, a piece of paper for your results, and a timer or chronometer. First, what you have to do is take your ruler and place it in a flat surface. Then, you have to put the domino pieces with 1 centimeter of distance between each other in the 13 centimeters of the ruler. After you have placed them, you have to make them fall, while taking the time and watching carefully what has happened. After the figures have fallen, you have to stop the chronometer and write in the piece of paper how long it took for the pieces to fall. Then, using less domino pieces, you will do the same. You will place them with 1 centimeter of distance between them in a flat surface, but only in 18 centimeters of the ruler. Then, make them fall and take the time and write it on the piece of paper. After that has happened, you will do the same that you did in the first step, placing 15 pieces of domino in 13 centimeters of the flat surface in a straight line with 1 centimeter between each. The difference in here will be that in one of the gaps that each domino figure has between them, you will place your hand, and while your hand is in there, you will make the domino pieces fall and take the time. After this has happened, you can observe that the distance traveled is different when your hand interrupts the travel. Record the distance and the time it took in the piece of paper. Now, you will do the same that you did in the second step. You will place 9 domino figures in a flat surface in a straight line with 1 centimeter between them. The difference here will be that 2 of the domino figures you will place an eraser horizontally. The eraser must have 1 centimeter between the domino figures. As you finish this, you have to make the domino fall again and take the time while they fall. As you can see, the distance of travel hasn't changed. Impressive, right? Now, for the last step of the experiment, you will place 15 dominoes in a straight line, in 13 centimeters of a flat surface with 1 centimeter between each. But you will part the dominoes in half, and in the middle you will place a toilet paper roll. Take away some pieces if needed, but there must be 1 centimeter between the toilet paper and the next figure. Make them fall and take the time. The distance has changed again, so you must record that in the piece of paper, how long it took, and how much distance they traveled. The question here is how will the velocity in which the dominoes fall change if we interfere with them or not by using different objects. My hypothesis here will be that if we interfere with the fall, there will be no change in the velocity or time that it will take the domino figures to fall. We think that the total displacement will be affected, but the time will be the same in all of them because the speed will also remain the same. Now, remember the data you recorded about the time and the distance traveled that changed? You will put them in a table like this. As you can see, it has the number of try, the distance of travel, and the time, but it also has speed. How did I get this? Well, you will have to use a mathematical model of speed, which is distance over time. The distance that will be used to get this is the distance traveled, not the total distance, because the travel was interrupted by an object that we placed. If you're willing to, you may change the velocity to meters over seconds, because when you first get it, you will have it at centimeters over seconds. Now, using the table, you can also do a graph like this that explains the change in velocity over time. The analysis of my results is the following. As you can see, my hypothesis was proven wrong, but partially wrong, because I thought that if we interfere with the fall, there will be no change in the velocity or time that it will take the domino spheres to fall. We think that the total displacement will be affected, but the time will be the same in all of them because the speed will also remain the same. The distance traveled also changed, and that impressed me very much. It was unexpected, but thanks to this, the velocity changed, and it's even more clear that the velocity changed. And all of this proves that the Newton law, the law of inertia, which states that an object movement will change if interfered only. It's true. In conclusion, my hypothesis was proven wrong, and the results weren't expected, but they proved the phenomena that we were using. I would like to add some recommendations for posterior makings of this experiment, like using smaller objects so the distance isn't affected and it's continuous and that there's a more visible change. But overall, I think that this experiment was done well and I'm quite satisfied with the outcome.